Let's go through the test, just focusing on part B, the short answer. We'll work through a couple of solutions and you can pause the video at any point if you need to. Right, so our first question here, when heated in air, magnesium ribbon reacts with oxygen to form magnesium oxide. So we'll just pop down magnesium is plain magnesium metal, oxygen gas, and magnesium oxide. We know that compound. We actually did that prac in class. So if you've forgotten though, this is a crucible, the piece of equipment that we would heat it in over a Bunsen burner on a tripod and gauze. So over quite a strong heat to react. Calculate the amount of magnesium in moles that was used. So let's go back to our question. So we've got some information here, got how much the crucible weighs with some magnesium before you heat it, and then the product, the magnesium oxide that you make. So if we want to know the moles of magnesium, we need this mass of the magnesium in the crucible, and then we're going to have to subtract the crucible so that we just get the magnesium by itself. So they're the two values that we need. So the mass is going to be that 53.726 minus that 47.372. So it's a little tricky to see there, moving between the data and the question. But if we just pop that into our calculator, we get 6.354 grams. That's the mass of magnesium. Then, of course, converting that to moles, we divide mass by molar mass or atomic mass for magnesium. So we take the 6.354 grams and have a look at our periodic table and see that magnesium weighs, where is it? There it's 24.31 grams per mole. So if we divide our mass of magnesium that we had in our crucible over our relative atomic mass, we'll get the number of moles of magnesium. So 0.2614 moles. My calculator has given me more decimal places than that, but I need to stick to 4 significant figures because that's the limiting number of figures I have in my question. So my answer should match that. All right, so that's how much magnesium was in my little crucible there. Now, the next question is to determine the percentage uncertainty. So I have to have a look. This one's specifically about the product. So the product's the magnesium oxide I made, and I also need to work out, so I need to find the mass of that product and subtract the mass of the crucible again, because the crucible is just the equipment that it's held in. So 56.941 grams is the amount of product, and then 47.372 grams is just the crucible and the lid. So if I find the difference, I'll find the mass of magnesium oxide, the product I made. And then my uncertainty, every time I took a measurement on the electronic balance on the scales, there was an uncertainty of 0.001 grams. That's a plus or minus value. So that's there, highlighted in purple. Now that uncertainty appeared twice because I had to weigh the crucible before and after. So I actually need to double that uncertainty. So that gives me a plus or minus value of 0.002 grams. Now that's an absolute uncertainty. If I find that as a percentage of the mass of the magnesium oxide, I need to put that 0.002 over the 9.569 grams that the magnesium oxide weighs. And then I multiply that by 100, of course, to turn it into a percentage. So I'll just color code those. I'll highlight in pink so you can see the mass of magnesium oxide, and in that sort of blue color or lavender, the uncertainty of my equipment. So we always take our uncertainty and divide it by our measurement and multiply by 100 to give us the percent uncertainty. And that's only got one significant figure there. Most uncertainties do because they're usually a single digit plus or minus value. Okay, the next bit, assume the reaction is the only one occurring and goes to completion, but some product has been lost from the crucible. Deduce the percentage yield of magnesium oxide. Okay, percentage yield has got to do with comparing how much you'd theoretically get and how much you actually got. So theoretically, the amount of magnesium oxide you should be able to make depends on how much magnesium you put in the crucible. So we take the moles of magnesium, which we actually already worked out. So if you go back up to your question up the top here, so have a look there, 0.2614 moles. That was the amount of magnesium you put in the crucible before heating. So we can just use that value, 0.2614. The amount of magnesium that we put into the crucible should be a good predictor of the amount of magnesium oxide you'd be able to make. Because if we actually write out a balanced equation, so our magnesium and our oxygen in the air react to form magnesium oxide. And if I balance that out, my oxygen is a diatomic molecule, so I need 2 magnesium oxides there, which means I need 2 magnesiums. That's balanced. But the critical thing here is that our ratio of magnesium to magnesium oxide is a ratio of 1:1. So that means the moles of magnesium should tell us the moles of magnesium oxide. So the mass of magnesium oxide I should be able to make is that number of moles multiplied by the molar mass of magnesium oxide. So that's the atomic mass of magnesium off the periodic table and the mass of oxygen. Okay, so my actual yield, the actual amount of magnesium oxide I made, I did in part B. That was the mass of magnesium oxide, the product in the crucible minus the empty crucible. The product was magnesium oxide and we made 9.569 grams. So my percentage yield then is what I actually measured of magnesium oxide divided by how much I expected to make based on the moles of reactant I put in. And again, being a percentage, like the last question, you have to multiply your answer by 100 to convert it to a percentage. About 90.79%. All right, and the next question is more just thinking about why you might have lost some. So if none of the magnesium oxide actually came out of the crucible, like there was no ash lost or went out into the air, maybe it's because some of the magnesium oxide was a bit tarnished, a bit oxidized already. So it wasn't pure magnesium to start with. That would give you a lower yield. Just be careful of suggesting things like soot deposits on the outside of the crucible, because that would actually make the crucible heavier and make you think you had a bigger yield, which does not answer the question because you're asked why the yield was lower than expected. All right, on to question 2. This one's about airbags in cars. So if you can't picture that, there they are. And the guanidinium nitrate compound is a little solid sort of powder that's in there. It's certainly not already a gas because it's got a very, very small volume at this point. And the decomposition means it will just break down without another reactant. So often they have other catalysts and things, but it doesn't react with another compound. And it makes nitrogen gas. So we use gas, water vapor, vaporization. That means that the water is also a gas. And then some carbon powder. And then, of course, you go back and balance our equation. Now, that guanidinium nitrate's a little more complex than maybe some of the compounds you've seen, but our nitrogen here inside the brackets, we've got 3 outside, and then we've also got the nitrate, so there's actually 4 nitrogens altogether. So we balance that out. The hydrogen, we've got 2 inside the brackets and 3 on the outside, so there's 6 hydrogens there. So balance out our water over here, 3 water moles over there, and go back and check our oxygen. 3 oxygens and 3 oxygens on the other side. Okay, that's correct. And our amount of carbon is correct. We've got 1. And our nitrogen, we're all balanced and we've got the correct state symbols. Now, the state symbols are quite important because actually moles of gas, what inflates the airbag, is critical to this next part of the question. So if there are 2 moles of nitrogen gas and 3 moles of water vapor gas, there are 5 moles of gas altogether for every mole of guanidinium nitrate that decomposes. So calculating the total number of gas for 10 grams of guanidinium nitrate means we have to then convert our 10 grams into moles. So we take our mass, 10, and just to speed things up, instead of writing out all those compounds individually, I'm just going to pop them into my calculator. I've got 1 carbon, 4 nitrogens, 6 hydrogens, and 3 oxygens. So I'm just going to plug them away and find my molar mass is 122.11. So the number of moles, 0.0819, that's the moles of guanidinium nitrate of the compound in the airbag at the start. And I have to multiply that by 5 because I get 5 moles of gas. So my answer is 0.409. That's the moles of gas of both nitrogen and water vapor combined. I need that answer to do the next part of the question. So what's the pressure of this gas in a 10 litre or decimetre cubed airbag at 127 degrees Celsius? Now, if you stuff up your last question, don't worry, you won't get penalised twice. If you just use your answer and it's wrong, as long as the rest of your working is correct, you'll get the next mark. So examiners use that abbreviation ECF. But let's go back, let's grab it. So we said it was 0.409 moles of gas being made. So we'll use PV equals nRT because we've got information about volume and temperature and moles, and we can use R from the data booklet, and we're solving to find pressure. So I'll rearrange that equation to make pressure what we're looking for, and then substitute in our values. So our moles from our last question, or if you just couldn't even answer it, put the number 1, so at least you've got something to work with. 8.31 comes from the data booklet. That's the gas constant. The temperature, just watch out, it's got to be in Kelvin, so make sure you convert it by adding 273 to Celsius, otherwise you'll get the wrong answer. So we've got 400 Kelvin here, and then our volume is our 10 decimeters cubed. Our standard units are meters cubed and pascals, but as long as we use decimeters cubed and kilopascals together, that's fine. So we get an answer of 136 kilopascals for the pressure of that airbag. The next bit suggests why water vapour deviates significantly from ideal behaviour. It's still a gas, just so be careful not to say that it becomes a liquid, but it does behave a bit more like a liquid as it cools down, as it loses kinetic energy. Some of these intermolecular forces, particularly in water, because it is a polar molecule, we see that actually there's a noticeable effect. It's actually quite significant, and it condenses, it contracts and becomes a smaller volume than expected for an ideal gas, where we assume there are no significant forces of attraction. All right, onto our titration here. We're taking some yogurt drink. So we're taking aliquot, which is a sample of something we're trying to measure. That goes down into our conical flask. We put that in there. And then what we're titrating it with, our sodium hydroxide would go into our burette. And then we take readings. So initial reading would be somewhere along our burette there. We'd record the volume, and it would go down as we put some into the conical flask. We'd take a final reading, and then our tighter volume is the difference between those. So we can calculate that from the table they've given us. All right, so let's just pop those underneath the table so we can see what we're working with. So these are the volumes that we've measured, because our first question asks us for the mean, which is the average. Now, there's a hint here. It tells you to use concordant results, which an exam question might just assume that you'll do anyway. You're expected to only use concordant values for a titration, which means the values that were within 0.1 of a centimetre cubed or 0.1 of a milliliter. So we would only include the concordant values when finding our average. So there are 3 of them, so divide them by 3, and we get 12.15 as our mean titer volume. And that's what we're going to use in our next question. And like before, if you get it wrong, it doesn't matter. You'll lose that mark, but if you follow it through correctly, you'll get error carried forward. So our moles of sodium hydroxide in that titer, in that amount delivered from our burette, we have to use the volume and we have to use the concentration of the sodium hydroxide that was told to us in the question. So that's there, highlighted in yellow, is our concentration, and then also what we've just figured out is our volume, because we need to use the formula N equals CV. So moles is concentration multiplied by volume. So we use those values. Our concentration, 0.100 moles per decimeters cubed, and our volume. Now our volume's in centimeters cubed, so just be careful with that one. But we use, there it is, our 12.15. So to convert that to decimeters cubed, make sure you put that 12.15 over 1,000. You can write that, or you could just do it first and put it into decimeters cubed, as long as you're doing that unit conversion to get the right result. So if we solve that, figure that out, we get 0.00122 moles, or if we write it in scientific notation, 1.22 times 10 to the minus 3. Okay, the next part. So what's the concentration of the acid in our drink? Well, if we know the concentration of the sodium hydroxide, we can see that they react in a 1-to-1 ratio, our lactic acid and our sodium hydroxide in our scenario here. So the moles of lactic acid in our aliquot, in our little sample in the conical flask, should be equal to the moles of sodium hydroxide in our titer. And we've just found that out in the previous question, how many moles of sodium hydroxide we used. So the moles of lactic acid, if we use C equals N over V, the moles of lactic acid is at 1.22 times 10 to the minus 3 over the volume of the aliquot, which was 10 centimetres cubed. Or we can just go straight to writing 0.0100 decimeters cubed. And then we'll get our concentration, which ends up being 0.122 moles per decimeters cubed. And all my units match. So that's good there. Okay, the other part of the question is about finding the formula of lactic acid, and look, it's actually over there in the question. So it's a bit of a hint there, but if we're going to do it mathematically to show you how to work out the empirical formula, set up a little table and find is easiest. So we've got carbon, hydrogen, and the remainder oxygen. And we can just treat our percentages as masses if we just were to think of it as being a 100-gram sample of lactic acid. If we had 100 grams of it, then 40 grams would be carbon. So we'll put 40 in there, our 6.71 hydrogen, and then those two values subtracted from 100 gives us oxygen, our remainder of our full percentage. Okay, and then once we've got our masses of all our elements, because they all have different relative atomic mass, the AR, so they're the values off the periodic table, we'll have to divide the mass by the relative atomic mass so that we can compare the moles of each element and get a ratio. So 40 divided by 12.01 will tell us carbon. 6.71 over 1.01 will tell us our hydrogen, and our oxygen we do the same, our mass over our relative atomic mass. And you can probably see straight away a pattern appearing here with our ratio, or if you need to do it with your calculator, all your values for your moles, divide them all by the smallest one that's there. So we'll divide all of them by 3.33. And so we get a ratio then of 1 to 2 to 1 for our elements, which means our empirical formula is carbon. We don't need to write the 1. Hydrogen, we put the 2, and oxygen. So CH2O is our empirical formula. Now, our empirical formula, if we added together the masses of each of those elements, 1 lot of carbon, 2 lots of hydrogen, and 1 lot of oxygen, the empirical formula mass would be about 30. And we're told in the question that the molecular mass is about 90, which is about 3 times as much, which just means we take everything in our empirical formula and triple it. So our carbon, we now have 3 of. Our hydrogen, instead of 2, we've got 6. And our oxygen, we've got 3. So again, looking at what those values would be in our empirical formula and seeing that our molecular mass is 3 times the empirical formula mass. And that's why we need to triple everything.